All right, let's get into it. Today, we're cracking open a classic problem from the Irodov physics book. Now, if you know Irodov, you know these problems can look deceptively simple, but there's almost always a clever twist. Let's dive in and see if we can spot it. You know the feeling, right? You look at a problem, it seems totally straightforward, but then you get an answer that just feels wrong. Well, there's often a hidden catch, a common misconception. And in this breakdown, we're going to find and dismantle one of the most common traps in basic mechanics. So here's the official problem. We've got a rubber cord, length L, just hanging there. At the very top, there's a little sleeve with mass M. We just let it go, and it falls. Our job is to figure out the absolute maximum distance that cord stretches. Sounds simple enough, doesn't it? Okay, before we even think about writing down a single formula, let's do the most important thing first. Let's visualize exactly what's happening. If you can play a clear movie in your head, the physics becomes so much easier. So let's break down this little journey. First, the sleeve is just sitting at the top, at rest, and the cord is all loose. Then, it's in pure freefall for the entire length of the cord, picking up speed the whole way down. The moment the cord goes taut, it starts to stretch like a spring, slowing the sleeve down until for just a split second, it stops at its lowest possible point. And here it is. This is the heart of the problem and the place where so many students go wrong. There's a huge, huge difference between the point where the sleeve would hang peacefully and the point it reaches after falling. Seriously, what's your first instinct here? When that sleeve reaches the very bottom and stops moving, even for an instant, it's so tempting to think, aha, it's not moving, so the forces must be balanced, right? The upward pull must equal the downward pull. But is that really what's happening? This slide lays out the drop perfectly. On the left, we have static equilibrium. This is where the sleeve would hang if you placed it there gently. The spring force, Kx, perfectly balances gravity, mg. But that's not our situation. On the right, at the lowest point of the fall, yes, the velocity is 0 for an instant. But because it had to be slowed down from a high speed, the upward elastic force is now much, much bigger than gravity. The net force is pointing up. So why is just balancing forces the wrong approach? It's all about that initial fall. The sleeve has a ton of kinetic energy by the time the cord even starts to stretch. It's moving fast. It doesn't just stop at the equilibrium point. It blows right past it. It overshoots it, stretching the cord much farther. So, if we can't just balance the forces at the end, we need a more powerful tool. We need a way to connect the very beginning of the motion to the very end without worrying about the complicated changing forces in between. And our hero for this problem is the law of conservation of energy. It's the perfect tool for the job. Why? Because the only forces doing work here are gravity and the elastic force of the cord, and both of those are what we call conservative forces. This just means that energy isn't lost. It just changes form. The total amount of energy in our system stays the same from start to finish. It's that simple. Okay, so let's do what I like to call an energy audit. We're going to make a little balance sheet for the energy at the very start and the energy at the very end. Let's walk through this table. At the initial state, when we just let the sleeve go, is it moving? Nope. Kinetic energy is 0. Is the cord stretched? Nope. Elastic energy is 0. It only has potential energy due to gravity. Now, here's a key step. Let's define the lowest point, the point of maximum stretch, as our ground level, our 0 for gravitational potential energy. That means at the start, it was a height of L plus x above that 0 level. So its initial potential energy is mg times L plus x. Okay, now the final state. At the very bottom, it stops for an instant, so kinetic energy is 0 again. It's at our chosen ground level, so gravitational potential energy is 0. All of that initial energy has been converted into elastic potential energy stored in the stretched cord, which is 1/2 kx squared. Now we just invoke our beautiful law. The total energy we started with must equal the total energy we ended with. And what does that really mean in this case? It means every single bit of gravitational potential energy the sleeve lost as it fell was perfectly captured and stored as elastic potential energy in the cord. It's a clean energy transfer. All right, the physics is done. The logic is set. Now for the fun part. A little bit of algebra to solve for our unknown stretch, x. Here it is, our entire physical argument, boiled down into one elegant equation. The initial gravitational energy on the left equals the final elastic energy on the right. This is the key. Now, if we just move everything over to one side, you can see what we're left with. It might look a little messy, but it's just a standard quadratic equation for x, nothing you haven't seen before in math class. So we pull out the trusty quadratic formula. It's going to give us two answers, a positive one and a negative one. Since x is a physical stretch, a negative answer doesn't make any sense here, so we throw it away. We take the positive root, and there it is. That's our final expression for the maximum elongation. So we have this big, complicated-looking formula. But what does it actually tell us? Let's compare the answer we got to the one we would have gotten if we'd fallen into that static equilibrium trap. And this chart says it all. Look at that difference. The bar on the left, mg divided by k, that's the tiny stretch you'd get if you just hung the weight gently. The bar on the right is our answer, the dynamic stretch from dropping it. It's not just a little bigger, it's significantly larger. If you walk away with just one thing from this breakdown, let it be this. When an object falls and impacts a spring or an elastic cord, the maximum stretch is always going to be greater than the stretch you'd get by just letting it hang there. Always. And this isn't just some clever exam question. This is critically important in the real world. Think about designing a safety harness, a crane cable, or the suspension on a car. If you only design it to handle the static weight, the system will fail spectacularly the first time it has to deal with a sudden dynamic load. Understanding its difference is what keeps structure standing and people safe. So let's go back to that final moment. The sleeve has reached its lowest point. It stops for an instant. But we already established that at that point, the upward elastic force is way stronger than the downward force of gravity. The forces are not balanced. So what happens in the very next microsecond? Where does it go? Well, that question is the doorway to the whole amazing topic of oscillations. But we'll save that for another time. Thanks for joining me.